Hello and welcome to the Friday Afternoon Projects. This time I'm still creating a toy language with Python LLVM, but this time we'll be looking at parsing expressions. So last time we got to the point where we could take an expression, a single sort of line of algebra as it were, and get the individual tokens out of it. This time we'll be trying to put those tokens together into some sort of order and understand what's going on. To do that, we'll basically be covering most of what we need to build actually a parser, and including operator precedence, which is something which is normally the sort of more complex part of a parser. So by the end of this part, we should hopefully be able to understand our expressions. So as per normal, let's log into our development box. And this is where we left off last time, the first commit of the language, which could do the Lexer. So let's remind ourselves of what we could do. Make sure we activate the VM so that all our local Python modules are available, including IPython, importantly. I can't type today. Right, and here we are. We had the Lexing notebook, which, if we remember, could get all the way from a single expression to this list of tokens here. So we'll be making use of that, and we're wanting to build what's called an abstract syntax tree. So let's first of all just define that before we try to turn this into it. So create a new notebook, and we'll call this abstract AST nodes. And the abstract syntax tree is essentially a set of objects that we'll be creating, which represent in an abstract sense, the actual semantic nature of our language, as in it lets us reason about our language, and it's what we'll be using as the main data structure in order to actually generate code from our language. So as I said, today we're basically trying to get to the point where we can understand a simple sort of 7 plus 4 times 3 over 2 sort of expression, but we'll build on this as time goes on. So we'll just make a brief note about this. Right, the most simple form of AST nodes is going to be ones which represent our arithmetic expression. Now there is 3 things you can have arithmetic expression at the moment in our language. You can have a number, which is going to be an integer. You can have a unary operator, so the most obvious one of those is minus, so minus 7 is minus 7. And then you can have a binary operator, so 7 plus 6. So we just need to generate those 3 different objects to describe them. And again, I'm going to use subclasses of the name tuple. Make sure to import collections first before you try to tab complete, obviously. Now, the reason I've done a subclass is because actually I want to be able to print these out in a nice way. So if I just create the integer literal and print it out normally, it actually looks all right. But I'd like to be able to generate, for my own sort of looking later on, I'd like to be able to generate a JSON representation. And ultimately, we're going to be wanting to generate actual code from this. So this is why I've done subclass. So for the moment, we'll just generate add a toDict method, which will return a sort of Python dictionary, which in some sense describes this AST node. There we go, and we'll be able to use that to generate some JSON later on to make things nice. So let's add to that a unary operation expression. And we'll test this briefly by just creating one. I'll create one, an op here. It will just be a character that represents the operation. We didn't try to do anything clever, I think, with that. Not just yet, anyway. Well, that looks to be working, doing what we expect. And so the last thing we have is a binary operator expression. I've just remembered I haven't switched on keymon, so I'll do that for you now. So a binary operator expression, it's going to be very much like our unary operator expression in the sense it has an operator and a right-hand side, but of course a binary operation also has a left-hand side to it. Right, and that's all we need, really, I think for the moment. This should serve our needs. Let's just check binary op expression does what we think it should do. Yep, that seems to do the right sort of thing. So the parser is essentially something which turns the stream of tokens into instances of these objects. So let's create a new notebook called parser. Or parsing, maybe. And just make a brief note to ourselves what we're doing. So it sounds pretty simple, doesn't it, what a parser does? To correct our spelling there. So the question is, how do we do it? Well, the most obvious and easy thing to parse is an integer literal. And the way we'll parse that is essentially we'll just take in a token. So all parsers that will construct them with a stream of tokens. And actually, no, I think possibly the more sensible thing to do is to have a single source of tokens, which lets us get the next one and push it back. So in fact, before we start writing parsers, we'll just create something which lets us take tokens, push and pop them, and peek them from a set. In fact, actually, we don't need to do that. There's already exists something which lets us push and pop peek tokens called collections deck. But we also want to be able to save our state. So the reason I'm thinking ahead about this is later parsers will try to sort of roll back after any mistake. So for example, the most obvious parser will be sort of one or more expressions. And so we keep parsing until we run into a parse error where we can't parse any more expressions. And in that case, we want to put the tokens that we took trying to discover that we couldn't parse the expression back onto the stack of tokens. So I'm going to just create a sort of simple token stream or token stack class that lets us remember individual positions so that we can go back. Actually, we don't want to pop off. We want to be able to keep the set of tokens, don't we? Because we actually want to be able to restore back to some sort of state. We don't actually want to remove tokens from our collection. We want to just sort of serve the next one at any one time. So actually, we'll maintain a counter, I think is probably the sensible thing to do. And we'll maintain that counter as a stack of counters. So the current counter shows you where the next token is going to come from, but we can save that counter onto the stack and then carry on popping tokens and restore that counter later on. Now just occurred to me that if we have run out of tokens, we want to report that error to the user. So I think the best way to do that is to create a parse error exception object, which will allow us to flag up errors from the parser. And this will also take an optional set of tokens that will reflect the area of the code where the error actually occurred. Right, so here in the token stack, if we fail to actually get the next token, which will, if we try to get something off the end of that array, we'll get an index error, I think. And then in that case, we actually want to raise a parse error. But we don't have any token about it because obviously the end of the input has got no token association with it. So now the pop method is very much like the peek method, except for we increase the cursor as well. And we want to be able to push and pop the actual cursor positions and onto the cursor stack. So this will allow us to push it before we start speculatively parsing. And if that turns out to be a fail, we can pop it back off again. So let's try making the most simple parser we can, which will just parse an integer literal token. So a parser object will always take as its input a token stream, token stack, sorry. And in this case, let's make a parser a base class. So this means that we don't actually need to do this little initialization bit here. We can elide that. So if we just make this member of parse base, then all we need to do is override the parse method. Now this will just get one token expecting an integer literal token. So we should probably just import all the token types from Lexing. And in fact, why don't we just add a little convenience method to the parser called pop expecting with a type on it, and this will pop the next token from the token stack, but we'll expect it to be of a certain type. I mean, this is going to be quite a common thing to do, so we might as well put it in the base class. And here we know exactly where the error that was, because it was in the token we just popped off. So we can make a useful, hopefully a useful error message. So an integer literal expression simply just pops expecting to find an integer at the end, and if not, it has a moan. And it just simply creates the integer literal AST node, so we should import the AST nodes module. Right, so let's see if we can test this. Let's get the lexer in. So create a token stack from the results of lexing that. We should have, in brackets, we have an error. Non-type has no attribute value. Look at this, we never returned the token. God. Okay, can we check it looks sensible? It has no options. We'll create a node attribute. So hopefully, if I get the node from this, there we go, get into the literal with the value of 5. And if we do plus, it fails because we're expecting unexpected token, was expecting integer, got a plus. Good, so that appears to work. So let's go back to making it actually work with a 5. So that's probably the most simple one we could get. So now let's try and get a unary operator. Now this is where we'll start to recurse, because a unary operator will take will expect either a plus or a minus followed by some expression. So let's just keep expression around as a variable, which points to the sort of the parsing class which currently parses expressions. So for the moment we've only got integer literal. Actually, that's not true, because we're about to. No. So let's just we'll create that in a second. But for the moment, let's just create the unary operator. So let's get the next token. Should be the operator, and check it's the right type. Okay, so that's got the operator out, and now we just need to parse the right-hand side. So let's check this works as we expect. Unexpected operator got token type integer. Oh, well, that's true, because we're we gave it the right thing, so that should be -5. We haven't. Of course, we haven't. Right. So far, the a unary operator can be a unary operator plus or minus followed by another expression, and our top level expression at the moment is this. So this will allow us to recurse. So that should hopefully. Unary operator got integer. Oh no, of course that that won't work at all. Yeah, let's say the expression is in literal, so that should at least get something else. That does, right, okay, so that's sort of got the right thing. So what we'll need to do, actually, we'll need to create a sort of primary expression parser that will parse one of either this, or the next expression which we're going to create, which is going to be called a bracketed expression, which will take brackets and then another expression inside it. So just quick test that. Not, it should do. No, it's node, not value, isn't it? There we go. And you notice how the bracketed expression just returns the subnode because there's only one node we care about. So although this exists in the parser, it won't exist in the AST. So now I want to create something called I think a primary expression. A primary expression will let you parse either an integer, a unary operator expression, or a bracketed expression. So I think the easiest way to do that is to just write one that tries to parse each in turn and see if it works. So in fact we just need to return that node like this. But if we got a parse error, so in fact before we do this we should try, this is where with the pushing and popping of the token stream cursor comes into its own, because now if for some reason this fails, we want to undo it, but we always want to undo it, because even if this succeeds, we want to undo the fact we just pushed that cursor. So I'm going to use a finally thing here, which means that even if it succeeds, we'll still pop the cursor. So this is just sort of pushing the cursor just in case this fails. But if it succeeds, it'll pop it anyway and get us back to exactly where we were, and we can try the next one. So let's make a comment about this. So if we don't manage to parse the integer, let's do the same thing, but try to parse a unary expression. So already I'm noticing that this should be refactored together in a try to parse function. Now I could just return none from this rather than trying to return this pair saying the node and then a success flag, but I'd rather return the success flag explicitly, because I think that way if we accidentally write something that returns a non later on, this won't actually sort of do weird and strange and odd things. We'll get the non propagating all the way through, so we see our error as soon as possible. So in fact actually that should take a parser class in here and do that. So now this should return non and false, and this should return that and true, and finally we also pop. Right, okay, so and in all cases we actually want to return the return value, not just return in general. So if we get here, we've completely failed. Right, okay, so let's just see if that works. So primary expression, we should be able to parse an integer, unary or bracket expression. And also, here where we recurse in this unary operator expression, this actually unary operator should now, instead of expecting an integer literal, should expect a primary expression. So currently our best expression node is in fact this primary expression. So let's see if this works. So that should still work. In fact, there. So what have we got here? Primary expression object has got no attribute token stream, because it's token stack. Why did I type token stream? My God. I think it's because I was originally thinking it would be token stack, a stream, but then of course it's not a stream at all. So that and that needs to be fixed. Okay, has no. Oh, have I failed to fix one somewhere? There, in fact. Expected unary operator got token type left paren. So why has the bracketed expression failed there? Ah, no, of course we don't want to pop the cursor if I was completely wrong up here, completely wrong. We don't want to pop the cursor at all. We want to essentially forget that we pushed it. So so we need another thing up here instead of pop cursor, sort of something other than push or pop. Actually, for the sake of, we'll leave it as is actually, because that's going to fill up this stack as we go on parsing. But this is only sort of a toy language, and so I'm not too worried about complete memory efficiency. But what that means is that we do want to pop the cursor if there is a fail, but we don't want to do it in all cases. So this slightly annoyingly will sort of fill up the cursor with cursor stack with one item per token, but we've already got a list with one element per token, so one integer per token. That's probably not going to be too awful. We can try and tidy it up later on, but for the moment I just want to get it working. Okay, so that's worked. Does that work? Unary operator plus with a 5, that's right. And then minus 6 or 56. Oh, we haven't implemented binary operators yet, have we? Whoops. But we should be able to do minus plus 5. Yeah, there we go. That does the right sort of thing. Right, so we have one thing left to do, and that's a binary operator. And this is a bit more complicated. So we're going to need to work out how to write a precedence parser. So let's sort of write the stub of this. And now I'm going to quickly read the Wikipedia page on operator precedence parsers. Look, here we go. This is what we want. So some pseudocode that actually does it. So we need to work out a precedence for each operator. So I'll code that into this here. So the highest precedence operators are the ones that sort of bind the closest. Now, in normal sort of BODMAS rules, what that means is that the higher the precedence, the closer it is to the front of BODMAS or whatever it is, the mnemonic that you remember from school. So we already have brackets working elsewhere. So the next thing is going to be sort of multiplication and division. So they're going to have, let's give them so that the lowest operator precedence is going to be plus and minus, isn't it? So let's give that let's give them 20. And then make the multiplication ones bigger. I'm putting some gaps in because really it doesn't really matter about gaps between them. And this will allow us to add some other things later on. Right, so what's the algorithm? So return parse expression 1 with the parse parameters. Right now, primary expression is we've already got a parser for parsing primary expressions. It's called primary expression. Kind of why I chose the name, because I heard that primary expressions are the sort of thing that just underneath binary operators are called. We want to primary. So what I'm going to do now is I'm going to basically transliterate the Wikipedia algorithm here straight into Python. So I'm going to try and do anything clever, so I'll speed that up a bit so you can see that running before your eyes. Right, okay, so that's just transliterated this code one-to-one. So read the Wikipedia page if you want to work out how that works. And shall we cross our fingers very much and hope it works? So now our highest sort of order expression should be binary expression. And so let's see if we can parse it. Binary expression. Oh, I've done the token stream thing again. Okay. Stack. Right. Oh, a bit more of an error. Carry on going. Name of the parse expression is not. The name parse expression is not defined, and that's in this one. Returned. Oh, that's because it takes 2 positional algorithms, but 3 were given. That's because I forgot to do self here. Has no I've done token stream again. I can't believe how much. Obviously, my brain really wants it to be called token stream. And I wrote this myself, so I've got everything. Expected unary operator or GOPREG, token type integer. Oh god, right, what's going on here? So it's trying to parse So after a lot of fiddling around, I found out that the reason for the error is because this is sometimes being called at the end of the input, which is, I suppose, sensible because it's got to the end of the input and it's trying to work out whether it's got another binary operator after it. So this is now going to explicitly catch the index error when we try to find this and just say, no, we don't have another binary. There we go, so it's actually got everything out. So I'll remove all this debugging print that I put in. I probably just cut out all of that fingering around, not knowing what I was going to do. Right, okay, so we get a primary expression no doubt, and hopefully has no expression. Does it not? Oh, that's because... What? Oh no, we need to, of course, this thing here we actually need to, that needs to be the node. There we go. So we get minus union op 5. Okay, so now we should be able to get a binary operator out of this. 5+2 fail. Taking seconds, no value. Oh, I bet it doesn't. No, it doesn't. It has token. What? I think op token is a token stack. Op token is because I'm not actually trying to look at the next one. So let's pop. Gosh, I'm astonished that worked at all. Good. So nearly right, except for the right hand side there. We need to take the node. So right hand side equals pass expression, and we need to take the node out of that. No, so this should return a node. What is that? Oh, because that should... there. Right, okay, there we go. We've written a parser. It's a bit complicated here with the binary expression and a bit of debugging to take it out, but it's mostly a transliteration of the Wikipedia page. So let's just see if this works. So 4 times 5 plus 2 times 3 times 2. The timesing should be done first, and then the adding should be done afterwards. And hopefully we should be able to bracket this. There we go, 2 plus 1. So we can make this a bit nicer by... Oops. And now this toDict thing is not doing the right thing, because of course here we're doing this, we need to actually call toDict on all of these. Silly. So save that. I have to restart the kernel to actually import everything. And then run all, and we should get something sensible out here. There we go, look at this. Excellent. And we only want to do this. This is a whole sort of Python trick to make sure this only actually happens when we're running this interactively and not when we import it later on. Okay, so that seems to work. The last thing I want to do just before we finish off today is if I try to do this, and try to put some white space into it, you see we get 5 times 4 and then we stop parsing because we don't recognize the white space token. So we actually just want to modify our lexer so that we skip all white space. So let's make a white space skipping. And we're going to do this by simply just writing a wrapper generator around the lex raw function. So you see here that it's a really simple generator function. It just wraps lex raw, but it silently ignores any white space tokens. And we've just reassigned what lex is here, so that now when we run lex, we actually get 3 plus 7. So I'll save that. Again, I'll restart this so that we pick up the new lexer. And there we go, we've picked up the same thing. So I think that'll do for parsing today. So let's commit this. We don't want that PyCache thing. I'll add that to the ignore list. So let's actually commit this in stages. So the lexing changes are just white space. Let's add the AST nodes. And finally, we'll add our parser. So I think that's the end of this part. I think we've done everything we need to do here. Join into the next part where we'll actually be adding some LLVM stuff to the abstract syntax tree, which lets us actually calculate the value of these expressions that we've just managed to parse. I know it's been a bit complicated, this one, and I hope you've managed to stay through it. Really, the most complicated part has been writing the binary operator expression, and for that I essentially just transliterated the operator precedence parser from Wikipedia. Okay, see you next time.